Okay, so as I was saying, okay, today we will finish up the last part, which is on pedostatic tube. So pedostatic tube is also a kind of flow meter. All right, this pedostatic tube is usually used in aircrafts. All right, so this tube here will be able to measure the aircraft velocity. Okay, of course it doesn't directly measures the aircraft velocity. What it does is it measures the relative air velocity. So from the relative air velocity, you will be able to determine the aircraft velocity. Okay, so how is it able to do that? Okay, one of the important concept here is that it's able to measure something called the stagnation pressure. All right, it is able to measure the stagnation pressure. So what is the stagnation pressure? All right, so if we look at this diagram here, okay, there is a standard open manometer. Okay, so this is an open manometer, and this manometer will give us a reading. But this reading here indicates the static pressure. Okay, it only indicates the static. Oops, sorry, why am I? Okay, so this open manometer indicates the static pressure. All right, whereas this thing, okay, this L-shaped looking thing, all right, this is actually a pitot tube. Okay, this thing here measures the stagnation pressure. So what is actually the difference? Okay, so if you talk about pressure, all right, from our Bernoulli equation, all right, actually pressure consists of two parts. All right, one is the static pressure, and the other part is the dynamic pressure. All right, so this static pressure, okay, is the P that we measure using our open manometer. All right, so this height here indicates the static pressure. All right, but the dynamic pressure, all right, is given in the form of half rho v square. All right, this v here, okay, maybe I shouldn't use the v. All right, this maybe I'll change this. This should be c. Okay, half rho c square. Okay, half rho c square. So this c is the velocity of your fluid. So this P plus half rho c square is actually your total pressure. Or we can call it the stagnation pressure. P stack. Okay, so what this L-shaped pitot tube does is that it brings the flow to a stop. It brings the flow to the stop such that the velocity here at the tip is equal to 0. Okay, so you see, because energy is being conserved, so if you bring the flow to 0 over here, so what you're actually measuring is the stagnation pressure. So if let's say I compare this point here, this point 1 and this point 2. Correct. So because energy is conserved, we can say that P1 is equals to P2. All right. And P1 will consist of P plus the half rho c squared. 2, okay, because you have already brought the velocity to 0, it will only consist of P. Okay, and this P that we are measuring at point number 2 here is actually the P stagnation. Okay, so this is the concept of a pitot tube. Okay, what the pitot tube does is it brings the velocity to 0, all right, such that what I'm measuring over there, all right, is the stagnation pressure. Okay, the full pressure that consists of both the static and the dynamic. Without a pitot tube, I say again, without a pitot tube, we are only at most able to measure the static pressure. We will not be able to take into account the velocity component. So only an open manometer will only be able to measure the static pressure, whereas a pitot tube, okay, is able to measure the total pressure, or in our context, the stagnation pressure. All right. So usually, these two tubes, this open manometer, and this L-shaped tube, all right, is connected together. So we call it a pedostatic tube. Okay. So a pedostatic tube will look something like this. Okay. So today, all right, the concept is the same, but we want to measure two things at one go. Okay, we want to measure two things at one go. All right, so the point number one here, okay, the outside one is actually measuring your static pressure. Whereas point number two here is measuring your stagnation pressure. So you can see that one is connected on the outside and is being linked to this side of the manometer. Two is the core of the tube and it's connected to this. All right, so there will be a difference, okay, in the height of this manometer. Okay, so what does this difference represent? What does this difference represent? So if you understood what I've said, all right, so again, you see P1 is going to be just the static. All right, P2, it is the stagnation pressure. So it consists of the static plus the dynamic. So the difference between P1 and P2 is simply P dynamic. And what is the formula for P dynamic? The formula for P dynamic is half rho C square. So this height difference here, okay, you are able to correlate to half rho C square. Okay, and the C here is what we are looking out for because we want to measure the flow speed. So if we can get this difference, all right, we can equate it to half rho C square. And then we will be able to find out the velocity. And from the velocity, we will be able to find out the flow rate. Okay, so this here, okay, is the operating principle of a pedostatic tube. All right. So we can look at some formulas. All right. So we can apply the Bernoulli between 0.1 and 2. Okay. So if we apply it between 0.1 and 2, all right, we can cancel a few terms. So Z1 and Z2 is cancelled because they are the same. All right. C2 is 0. Okay, because this one, all right, is measured by the pitot tube. So if it is measured by the pitot tube, all right, it is the velocity is 0. Okay, so we can rearrange it. All right, we can rearrange it to C1 square over 2G is equals to P2 minus P1 over rho G. Okay, so we can cross multiply. We bring the 2G over here, and then we take the square root. All right, so by applying this Bernoulli equation, we can see that we can get the velocity of the flow, all right, by simply looking at the pressure difference between P1 and P2. So this pressure difference, P1 and P2, is measured by the manometer. all right, that is being connected. So this manometer that we have here, all right, will tell us the pressure difference. Okay, can? So same thing like all other meters that we have, all right, we have some kind of this coefficient that we need to introduce. Okay, this coefficient is meant for taking into account the losses, all right, and the calibration. Okay, so by adding in the C value here, all right, this is our coefficient of instrumentation. All right, then after that, we apply V dot is equals to AC. All right, and this will give us our final flow rate. Okay, so don't be confused. This C here is our coefficient. All right, this C here is our coefficient of the instrumentation. Okay, that is written here. Okay, so let's look at one example, example 5.5. So we have this water pipe. Okay, so we are asked to calculate the static pressure at 1, the stagnation pressure at 2, okay, the pressure difference between 1 and 2, and the velocity of the water in the pipe. Okay, so this example will reinforce what I've just said. So for point 1 here, okay, it is measured by the open manometer. Okay, so open manometer can only measure the static pressure. Okay, so very easy. We can apply P equals to rho GH. Okay, and so the rho is water, 1000 times 9.81 times your height. Your height is 10 mm. So 10 divided by 1000. All right, so this will give you 98.1 Pascal. Okay, so the open manometer, okay, can measure the static pressure at 1. Next, at point number 2 is the stagnation pressure. So stagnation pressure, all right, will be indicated by this height. Okay, so same thing, we are going to use the same formula, rho GH. Okay, so today, all right, let me get an eraser, see what I can get this. Oops. Okay, so for the stagnation, all right, we are going to do the same thing. We are going to calculate the rho GH. So today, this will be 1000 times 9.81 times your height, which in this case is 30 mm. Okay, and so if you calculate this, this will be 294.3. So as expected, your stagnation pressure is definitely higher than your static pressure. Okay, so the difference between 1 and 2. Okay, so the difference, all right, for part C, okay, will be 294.3 minus 98.1. Okay, so over here, this you will get 196.2. Okay, Pascal. So what is this difference? This difference, all right, is accounted for by the dynamic pressure that we have described just now. So definitely the stagnation will be higher than the static. Why the stagnation is higher than the static? Because the stagnation consists of the dynamic portion. So if you take the difference will be the dynamic portion. Okay, so to get the velocity, okay, we can apply the equation just now, which is square root of 2g times P2 minus P1, all right, over rho g. Okay, so this will be square root of 2 times 9.81 times P2 minus P1, which is 196.2, divided by 1000 times 9.81. Okay, so this C equation, all right, is obtained by applying Bernoulli between 1 and 2, all right, which was derived just now. Okay, so the main thing here is to understand what is static pressure and what is stagnation pressure. Okay, the difference between them is static is just static. Stagnation consists of both the static and the dynamic pressure. Okay, and when you take the difference, you will be able to calculate the velocity of the flow. Okay, like in this case. So value-wise, okay, you can go through these numbers yourself, all right, which I've already shown also. Okay, so just to make sure you understand, okay, I will advise you to go through this calculation one more time. Okay. Okay, so next one, 5.6. So 5.6, we have a pedostatic tube connected to water manometer that's used to measure the velocity of airflow in a wind tunnel. Okay, for part A, we are asked to show the pressure difference. Okay, it's given by this. All right, where S is the specific gravity of air and rho air is the density of air. Okay, then we'll deal with part B later on. Okay. Okay, so we have the figure here. So we apply this manometer. Okay, so in order to find out the pressure difference, okay, because we want to find out the pressure difference between 1 and 2. Okay, one is here, the static part. Oops, sorry. Okay, 1 is here, the static part, and 2 is the stagnation part. All right. So to find out the difference, we need to apply the manometer principle. Okay, between 0.3 and 0.4. Okay, there should be a break here. There's a typo. So we must start off with P3 is equals to P4 based on the manometer, because the manometer concept says that the pressure at the same height of a same fluid must be the same. So P3 must be equals to P4. So how do we get P3? Okay, P3 is everything above it. So what is above P3? All right, P3, okay, what is above P3 is this portion, which is H. This portion, again, which we call X. All right, and also your P2, which is here. Okay, so everything above P3 is P2 plus PX plus PH air. Okay, so 0.3, everything above 0.3 is all this, P2, PX, and PH. How about P4? What is above P4? P4, same thing. We have PH, we have PX, and also on the outside here is P1. Okay, so everything above P4 is P1 plus PX plus PH. But in this case, the H here, all right, is filled with water. All right, so the fluid is different, so you must put it as water. Okay, so by applying this manometer concept, okay, you will get this formulation here: P2 plus PX plus P air rho air GH plus equals to P1 plus PX plus rho water GH. Okay, so the PX is the same, so you can cancel it. All right, so shift the P2 minus P1 to the left hand side. Okay, then all the other terms to the right. Okay, we factorize out the P air, the rho air, sorry. We factorize out the rho air, and inside becomes like this. Okay, so how do we change this rho water to rho air into 1 over S? Okay, so rho water over rho air. Okay, so we take the reciprocal of it. So this becomes rho air over rho water. Okay, mathematically they are the same because I'm just taking the reciprocal. Okay, can. So what is rho air over rho water? This is your S, which is your specific gravity of your air. Okay, so this is how you convert your rho water over rho air into 1 over S. Okay, so once you convert it into 1 over S, this is your final presentation. Okay, so you have successfully represented P2 minus P1 in terms of your height. Okay, the H here is the manometer height. Okay, so once you have that, you can go straight into your calculation, okay, from part B. So for part B, we are asked to assume that H is 10 cm, density is 1.2. All right, so we are asked to calculate the airflow. Okay, so since this is a pedostatic tube, we'll use back the same pedostatic tube equation, which we derived from Bernoulli. All right, so the purpose of part A was to calculate P2 minus P1. All right, so this has to be placed inside here because remember, the idea of a pedostatic tube is to be able to measure the pressure difference. So this pressure difference will translate into your velocity. Okay, so I plug this in, I substitute this in, and it becomes like this. So the rest of the job is just to put in the numbers. So 2 times 9.81, rho of air is 1.2, 9.81. The height is 10 mm. Okay, so please change to 0.1. All right, then we have our 1 over S. Okay, 1 over S here, I wrote it as 1000 over 1.2. Okay, because this is basically your rho water over rho air. Okay, which just now we converted into 1 over rho air over rho water, which is your 1 over S. It's the same thing. All right, so but if you want to work out S separately, S is 1.2 over 1000. So 1 over S is basically 1000 over 1.2, which is what you see down here. All right, so minus 1 over this one, and you get your final velocity. Okay, Ken? So you must understand the working principle behind this pedostatic tube in order to make this calculation meaningful. Okay, Ken? So if not, I think that's all for chapter 5. All right, so sorry. Okay, so that's all for chapter 5. All right, so let me just stop the recording.